had the two-tailed test, and we had to, if you remember yesterday, we did the two-tailed, and we had to take our probability times 2 because it was for both tails. When we are talking about the two-tailed test, we can also use a confidence interval. What you do is you build the confidence interval, and if it contains your piece of 0, then you don't reject. If it does not, then we can reject. So we are going to look at an example involving confidence intervals, because in the last chapter we learned how to build confidence intervals. And if you have forgotten any of that, remember, you still have your formula sheet, and under the chapter 9 it has your confidence intervals piece. So a 2009 study found that 34% of teenagers text while driving. A more recent survey found that 353 of 1,200 randomly selected teens had texted while driving. Does this suggest the number has changed since 2009? Using 95% confidence interval to answer the question. Okay, we should always check our criteria on this. Let's see, would 1,200 be less than 5% of the population? Yeah. My N times P, what's my P? Times 1 minus P. So if I do that, and everybody has this notes handout, right? If you were on yesterday, so we get 269.28, which is most definitely greater than 10. So that's good. All right. Now we need to figure out what's the null and alternative hypothesis here.
The null is P equals 0.34.
It's the percent, so it's our proportion. We just want to know if it has changed. So the alternative would be P. It's not equal to 0.34. Okay, so we could do this how we did example 2 yesterday. But I've asked you to build a confidence interval to do it. So let's talk about our confidence interval. If you look on your formula sheet, our confidence interval for a p hat is p hat plus or minus b alpha over 2 square root of p hat 1 minus p hat over n. So we know that. I need to find some pieces of information to plug in here. My p hat is 353 out of 1,200. So that is 0.294167. My z alpha over 2, it was a 95% confidence interval, so that would be 0.05 over 2. So that's z of 0.025. So remember, what that means is on your normal table, you're trying to find 0.975 inside the table. And that is 1.96. So now I can plug into my formula, my p hat, plus or minus our 1.96 square root of p hat 1 minus p hat over n. What's my n?
1,200.
Well, I can fit this in. remember, once you type in one of them, you can just hit second enter, change your sign, and get the second one. So I get 0.26843199. So, if this contains our p-value, then we don't reject the null. If it doesn't, we do. Essentially what we found is we are 95% sure that the true proportion is between these. Okay, we are trying to decide if that true proportion is 0.34. Is 0.34 in this interval? No. So I am 95% sure it should be in this interval. Since this is not, then we would reject the null hypothesis. If I asked you to write a conclusion, so you would say there is sufficient evidence to conclude the proportion of teenagers who text while driving has changed. So this is just another way of doing the hypothesis test. A lot of this kind of hinges back to old stuff, you know, the z-scores and the probabilities, confidence intervals. It's all pieces we've done before. We're just using those things to now draw conclusions about our population. All right. Is this one okay? The last thing I want to talk about, I've been making you check the n times p times 1 minus p every time. And it's always worked. But if it doesn't, then we cannot assume it's normal. And what we have to do is go back to the binomial distribution that we used like 2 chapters ago. So if n times p times 1 minus p is not at least 10, that means it's not normal. We will use the binomial instead.
Remember that?
The binomial distribution, we had a couple options. The binomial table, that was the other packet that I gave you. So we have this one that we use all the time. The binomial distribution was a separate packet like this. Unfortunately, this didn't have everything. So we also had a formula that we could use to calculate our probabilities. The formula was in the chapter 6, and it was that n choose x, your p to the x, your 1 minus p to the n minus x power. So if we couldn't read it off the table, we had to use the binomial formula. Again, that's all on your formula sheet. You just have to know what you're looking for. In 2006, 10.5% of all live births in the United States were to mothers under 20 years of age. A sociologist claims that birth to mothers under 20 years of age is decreasing. She conducts a simple random sample of 34 births and finds that 3 of them were to mothers under 20 years of age. Test the claim at the 0.01 level of significance. Alright, so we have to check, would 34 be less than 5% of the whole population? Absolutely. Let's check the n times p times 1 minus p. So my n is 34. The p, what am I using for that? 0.05. When I do that, I get 3.195. That is not greater than 10. So this is not normal. Okay, so that means we are going to still do our hypothesis test, but we're going to have to use the binomial to do that. What is my null hypothesis? Okay, the alternative hypothesis, what does the sociologist believe?
It's less than
Alright. Let's find our... Okay. If I want to calculate this, if we were using a normal, we would take our p hat value, the 3 out of 34, and convert it into a z score, right? That would be our starting point. We'd find our p hat and we would do the z. For the binomial, we don't use z's, so I don't need to do that. With the binomial, we were just counting the x's. So what we need to do is look at that 3. We are trying to find the probability that or something is less than. That's our alternative hypothesis, less than. So let's find the probability that x is less than or equal to 3 to see if this is unusual or not. Because we can't do it on the normal table, we don't need to change it to a z, we need to use the binomial. Okay, my p is 0.105. Is that one of the probabilities given on my table? No, so that's not going to help me here. We can do it by hand using this formula that I gave you. So n choose x, you guys remember doing this? Choose 3. Then we had our p to the x, so that would be 0.105 to the third. 1 minus p, I'm just going to go ahead and subtract those versus writing that every time. That'd be 0.895 to the n minus p, or sorry, n minus x, so 34 minus 3 is 31. But that's just the probability of 3. I would also have to do the 2, the 1, and the 0. Okay. Let's type one of these in real quick, make sure we remember how you have to do your parentheses, 34, math, go over to probability, it's NCR, 3, 0.105 to the third, 0.895 to the 31st. And you would get like 0.2224. And then for the 2, you can just hit second enter. You're going to change your 3 to a 2. So it'd be 0.105 squared, and now it'd be 0.895 to the 32nd.
Shit, yeah, you have to change everything this time. I forgot to do that.
Yeah, you have to change all the powers. Then you do 34 choose 1, 0.105 to the 1st, 0.895 to the 33rd. And then you do your 34 choose 0, 0.105 to the 0, 0.895 to the 34th. And then we would have to add all those together. Now we are going to have some rounding error here. Okay. So what this tells me is, under the assumption that the probability is still 0.105, having 3 or less has a probability of 51.49%. Is that unusual? No. My alpha level here was what, 0.01? So since 5149 is greater than my alpha, we fail to reject. There is not sufficient evidence. To conclude, the proportion has changed. Okay. Here's the thing. That was a little time consuming, wasn't it? And what if I were talking about, 16 or less? Would you have wanted to add up all 16 of those?
Absolutely.
Not really. When we did the binomial, usually if it was one that I gave you by hand, I kind of made it small, and the ones where you were going to have to add a lot of things, I picked a probability on the table. But we know in real life everything's not nice, pretty probabilities, right? We can use our calculator for this as well. So, on the calculator, you are going to go to second the VARS variables. Then you are going to go down, what's it look like? Okay, it is on B, so you have to kind of go down your list. There are 2 binomials. There's PDF and CDF. We're going to do the CDF. The C stands for cumulative. If I went to the PDF, then I would have to calculate it for the 3, and then for the 2, and then for the 1, and then for the 0. If I go to the cumulative, when I do the 3, it will give me everything 3 and below. So it'll go ahead and add it up for me, so I only have to calculate once.
Is there a way to do it above?
1 minus.
Oh.
So then we're going to hit that. Okay. Now, it asks you some questions. Trials. How many trials did we have on this? 34. P, what was our proportion we were using? And our X, what X are we looking at? So then if you enter a couple times, it brings up your probability, and it says 0.51487, so 0.5149. Same thing we got when we did it by hand. So you are free to use this now. In the scenario where your n times p times 1 minus p is not bigger than 10, then we treat it as a binomial, and we do it this way. I think that might be like the very last homework question on that section. Alright, so what we've seen in this section, I've shown you how to do things by hand, but pretty much everything there is a shortcut on the calculator. You should know how to do it by hand, so try a couple of them by hand, and then once you feel confident that you know the procedure, if you want to use your calculator, you may do so. You've got the rest of the hour to work on homework and ask questions.